we have 3 lectures before spring break. And what I'd like to do is, rather than sort of continuing on with more clustering algorithms in general, I'd like to sort of take Nitin's demo from Tuesday as a lead off into another topic that is, I'm very conflicted here because it's extremely important, but it's also very boring. But I feel like we do need to know what, think of this as your healthy breakfast, not the junk food part of the course. So the issue of validation. And so if you have a supervised problem, a supervised learning problem, right? It's very easy to validate what you have because you have training data and you have labels. You have test data and you have labels for that as well. So you do a training test split, you run your algorithm, and once you run your algorithm, you can direct it towards the right answer because you know what the right answer is supposed to be. You have labels. In any unsupervised problem, by the very definition of the problem, you don't have the answer. It's unsupervised. You are trying to find stuff. And in many ways, there are people who will say this is the difference in data mining and machine learning, that in mining you're literally digging for stuff. You don't know what you're looking for. Whereas in learning, you kind of know what you're looking for. You just want to find a model to express that, what you're seeing, the pattern that you already observed. And of course, as the archetype of unsupervised learning, clustering has all of these problems. Right? How do you validate the clustering? And I think it is possible that you've already been seeing this happen, and you've been doing the assignments, and you've been talking about these problems in class. That I can design all these fancy algorithms, and I can define cost functions. But a cost function is only a proxy. Right? A cost function is a proxy for what you really are trying to find in the data. And hopefully by now you've seen that there's so many different cost functions that not any one of them is sacred. They're just all different ways of getting at what we want to get at. And when you say we're getting at something, how do we know we got there? There's really no easy way to do this, right? Unless you actually have an answer. And so we talked about this with the MNIST data. You have this notion of a ground truth and you want to compare against a ground truth, right? So that's one way to do it. So there's a larger topic of how to validate clusterings that is both very fuzzy but also very important, because at least you need to know what tools are available or how you think about validation as a general problem. And you actually have already seen one example of cluster validation, namely in the whole section on choosing K. Because you think of choosing K or as model fitting as one way of trying to validate your answer. Right? If you're trying to find the best K for your data, what you're really doing is searching for some kind of validation for what you really find. So there are some basic, very general principles for how you might validate a clustering. But they're so basic that they're not something that if I told you, you would say, oh, I never thought of that. In fact, I'm going to let you think of them right now. So there are a couple of different ways you could validate clusterings. And you're going to be able to come up with all of them in about 5 minutes. So go. How do you validate clusterings?
Classification.
Huh?
Classification.
Explain.
So you've got, if you have some known categories that your data belongs to,
okay,
then you can classify. You can see if, like maybe this through a majority, whether there's like most of your cluster lands with the same label or not.
Okay. So one idea for how to validate
different labels from the other ones.
Yes, right. So one idea to validate a clustering is via, let's say, labels. Labels given to you. Right, so let's say we'll do validation. So what you're saying is that you want to compare the clustering you get, let's see, to some reference. Is that what you're saying, John? You have some kind of reference because you have labels?
Right.
Yeah. We don't yet know how to do this, but we'll get to that. So you somehow have some reference. So this is almost like a supervision, except that you're not using the supervision to drive the process. You're using it to validate the process. Right? In classification, binary classification, the labels are used to guide the search for the best answer. We're not doing that here. We're saying just first find the answer, but then at the end check against what you might consider the right answer. And of course you've already done this, right? MNIST. So this was your reference. The digits 0 through 10 were 0 through 1, 0 through 9 was 0 through 9, and you compared that to what you got. Okay. All right. Suppose I don't have a reference. What do I do now?
Count the number of.
Sorry?
Count the number of clusters.
You count the number of clusters. I have 15 clusters. Now what?
Is it the same as the expected number of clusters?
How do you know what the expected number of clusters is?
Would be known.
How do you know that? Where's it coming from?
We would already, I assume that we already knew the number of clusters and then we run a clustering network.
So you're saying if you knew the number of clusters, but then you ran a clustering algorithm that looked for exactly those many clusters, you'd still get an answer, right? So if I said, okay, I know my data has 10 clusters.
No,
Now I'll run k-median with 10 clusters. I'll get a 10 cluster.
Clustering algorithm does not know the number of clusters in advance.
But most of them do. Most of the ones you've seen, in fact, require you to know the. So only a few that don't, in fact.
Yeah.
So while you're right that if you know the number of clusters, you can validate. You can't quite validate yet because you have many answers that are all 10 clusters, and there may not be enough. Yes.
But what about like in the case of the assignment where we were to come up with a case where k-means and both agglomerate clustering were similar? Can
Yeah.
you, in that sort of a case, basically say if these are actually spread out enough or distinct enough in terms of clusterings, comparing 2, 3, 4 different clusterings that you would assume would give you different sorts of clusterings based on what we know, and if they give you the same clustering, you can assume that that would be ground truth.
Okay, so this is definitely something different from before because we know that a reference. Your proposal is run different algorithms. So that they give you, let's say, they give you clustering C1, C2 up to Cn, and now compare them. If they all look similar, then you're happy, right? Good. This is a different way of doing it. Yes, absolutely. Okay, come on. We've got maybe one more thing to do. Then there's a whole chapter of this book we've covered. It took about 5 minutes. So there's another way of doing things.
Yeah.
Look at it.
What if you don't really care about the clusters? What if you just call it? What if you only want to have a property of the points that are close or in the space that are embedded?
Interesting. So expand on this a bit more.
What I'm talking is about finding the space to which to embed those points.
So what you're saying is that the way you want to validate this clustering is not by looking at the clustering itself, but by looking at some other property that emerges from the clustering.
Yes.
Is that right?
Yes.
Okay, can you give me a more concrete example of that? I think it's an interesting idea.
Yeah, I think let's say you want to search for anomalies. Not anomalies. Analogies, right?
Mhm.
So, woman, queen, man, king.
Okay.
Okay, and then you want the space in which those points are presented
Mhm.
is it's a well-formed place,
Right.
and it enables you to do this. And you can verify.
So how does the clustering give you the space?
But it's a very delicate notion of clustering now.
Sure.
It's not anymore assignment point.
Absolutely, but the clustering somehow gives you a
Yes,
space. How does
but
it give you that
Yeah,
space?
it gives you a space in such a way that the semantically, let's say, similar words would be together in this case, and that you require some kind of linear properties between those points.
Right.
Linear properties means subtracting or adding vectors.
Right. Okay, good. I'm going to take your idea, which is I think a very interesting point, and try to generalize it a little bit.
Yes.
Because I think there's a larger class of ways of doing validation, of which yours is one example. And I think this, sorry.
There's one I don't know whether it's common in computer science. We use jackknife a lot.
Okay. So
So-
jackknife is for cross-validation, yes?
It is for experimental designs also
Right,
sometimes
right.
to see whether results are stable.
Yes.
So can this be applied here where you remove some points and see the stability of your clustering?
Okay, good. So this, in some way, you can think of this as related to this second point. There we were trying to interpret stability as goodness, where stability was produced by looking at different algorithms. Here you're saying do like a dropout kind of thing, like leave one out or jackknife thing. Okay, good. So let me write that down as well. I think it's slightly different. And then we'll get back to Clement's point here. Okay, so here the idea is that subsample data and get C1 to Cn, right? And then compare them. Right. And I would say that both of these, right? And here you're doing a specific kind of different algorithm. relate to this issue of stability, which I will get into. Okay. Now the point that I want to come back to here, which I'll call number 4 right now. There's still number 5, by the way. So keep thinking. So I thought there were 3, but I think you come up with more stuff that's in the book. That's good. The general category here, and I was just talking to John about this before the class started, is that, as I've said all along, right, often clustering is the first step in a pipeline of tools you want to apply to a problem. It's not the last step. It's like a pre-processing step or a compression step or whatever step you want, or it's a geometry building step or something like that. And what you really have is some other task you want to solve after that. And maybe that task is a supervised task. You just don't know. So one way to evaluate whether a clustering is good is not by looking at the result of the clustering, but by looking at the result of the operation you're going to use that's going to use the output of the cluster. Right? So you have some kind of test problem. Maybe you're doing some kind of classification, or you're doing some kind of geometry building, right, or something like that. So you some kind of metric learning, or if you want to call it that. And you have some kind of classification task here, that's it, right? But in order to build the right space to do the classification task, is to build the right representation, you are doing a clustering step first. So your clustering somehow gives you a representation. So again, the assignment is not so much the issue as the fact that once you group points together, you can build some representation of the data from this, right? In an unsupervised way. And then you solve some task off of that. Hopefully that task is supervised. And so now you can evaluate the different methods you have here by saying, okay, I put 3 different methods here, and I look at how well they do on this task at the end. That's one way to check how well they do. It's not as satisfying because there's this one extra step here, and you don't know what kind of noise this process is introducing, and how much variability here is clouding out what's happening here. But it's one way to tell. If you keep this nicely controlled, then you can say, okay, if the only parameter I'm changing is this, and I get some different results there, that's one way to check what I'm doing is right. Right? So then again, you're not looking at the output of the clustering. You don't care about the partitioning. You care about what it tells you about the data that you're using later on. And there's some sense in which this is a better approach in many ways, because either you need a reference, or you are not looking at validation so much as stability and all. So there are arguments to be made that this is, for a particular task, you should look at what you're using the clustering for and use that as your validation. Okay, good.
So I just want to add something. So, it can happen. I'm not sure if it's in many applications, but it can happen that the representation that you end up building for that particular task can be used for many other tasks.
Yes.
So it's not necessarily just
Absolutely.
I'm just gonna do just for this one thing.
Right. So there could be other things that you do as well. And so the question of validation becomes more tricky now, because now maybe it's good for this, but not for that. Okay. Something to keep in mind if you have a problem when you're using clustering. Think of this as the kind of, I don't know anything about what's going on validation. All of these assume some kind of structure. You either have a reference, or you have some task, or you have different algorithms and you're looking for something else. What happens? Here's the case where you don't know anything at all. You literally don't know anything about it, except you just clustered something. Even in that case, there's some simple things you can try to do. So think about it this way. I just gave you a bunch of points, and I said this is the clustering of these points. So let's say the points are Euclidean space. They have some 10 coordinates each, and I tell you this is the clustering. Can you give me any sense of how good it is? Yeah?
Could we give within a certain degree of concentration or dispersion?
Can you explain?
So I guess it's still speculative, but
Sure.
You could perhaps infer greater concentration within each cluster.
So I want you to make them more precise. Any way you like.
The sum of the
Concentration. What is my concentration?
Okay. So the distance between each of the points that is classified in a given cluster.
Okay, so good. So let's say I give you a clustering. It looks like this. It looks like this. Now I look at this cluster here, and I look at, say, I don't know, the average pairwise distance.
Yeah.
Right. So let's call it D average. Okay. Now what do I do?
So
I have one for each cluster.
Yeah, for each one.
So 1, 2, and so on.
Right,
Okay.
and so on and so forth, so you'd have many more. And then you could perhaps look at the degree of dispersion.
What would that be?
So the
In the same
distance
language.
between each of the cluster centroids, or,
So for example, you could look at this distance,
yeah.
or you could look at this
Or the
average
outlier,
distance.
right.
You could look at the average D out between every pair. right? Okay, and then what do you do? What do you want? Which I've got all these measurements. What do I want now?
I think all we could say just
Some
minimizing
sort of
some
standard.
One second. Sorry.
That's pretty much as far as I.
No, but you got the numbers.
Which
But
is- right. so
What is
some
a,
sort
what
of-
number makes the clustering good? What number makes it bad? That's
Yeah.
how you do it. What do you want in your head?
Right. Well, you do. You want some sort of like average or standard by which to.
Yeah, but I'm willing to be very informed. I'm not
Qualified.
asking for a precise answer.
Yeah.
But at just a level of, big is good, small is bad, right?
Mhm.
What would you say here? What is the good direction? What is the bad direction?
Well, the great direction is concentration within each cluster and dispersion, high degree of dispersion between clusters.
Okay, so you want something like,
Yeah.
right? Where this is some kind of average over individual clusters, this is some kind of average across clusters, right? So this is this is a good thing, right?
Yeah.
That's all I'm asking. Some kind of notion like this.
Yeah.
You were going to say something?
Yeah, I think this fifth method can be just called we want to optimize or for some particular objective function, whatever it is. If you don't know anything about the data, you can say, oh, I don't know, D in, D out, right? Or I may want some other objective function, and I'll just treat it as an optimization problem,
Right.
and what comes out, comes out.
Yeah, the thing is that optimization problems, right, they have weird quirks, right? So we've seen things with k-means and hack and spectral methods, right? You can define optimization that you think should capture what's going on. But what you really want to capture is a bit more vague.
Yeah, but
So you can't optimize with respect to something vague, but you can evaluate with respect to something vague. You see what I mean? Right? In other words, I could convert this into a formal cost function and try to say optimize with this. It might actually be very hard. I might prefer a surrogate that's easier to work with. But then I want to evaluate with respect to something like this. And at some level, right, if you don't know anything else about your data, this is all you can say, that clusters should be tight and far apart. Right? If you think about the information theoretic view of clustering, that's what it was saying, right? I want clusters to be tight, and I want them to be far apart with the information, with the notion of far and tight being information theoretic. Right? And so, in fact, there are measures that basically say, so you look at this ratio, this ratio should be big. Right? There's something called the Dunn index, for example. There are various indices of quality of a clustering you can list out based on reasoning like this. And again, you can see, I take averages or take worst case. You can, there's a whole 18 different indices you can come up with based on different permutations and combinations of these choices. But they're basically the same idea. Okay, so that's actually, now we actually have a good collection of validation methods. So this one is generally called, this method here is called internal validation, I think for the obvious reason. Internal because it's an invalidation that's purely internal to the structure. And if this makes you uneasy, that's a good thing, right? Because it seems a little bit circular, right? It seems like, I'm evaluating it based on what I just computed, but obviously it'll look good with respect to that. That's why I said this is the difference between the measure you think you want and the proxy that you choose to optimize with. Right? The proxy could be k-means or k-median or hack or spectral or whatever. But then at the end, what you really want is this. So you obviously don't want to optimize with respect to the measure you're evaluating. Otherwise, then you really are being circular. You'll never get a bad answer. Right? What you want is something where you can do a cross-check. Right? They have two different perspectives of what's going on. Okay, so this is the internal method. In the literature, at least, this is what is called an external method. Again, for obvious reasons. Right? That you have some external notion of quality. And you can even think of this as being an external method. Right? You have an external notion of quality. And you're saying, okay, I am not going to try to justify the clustering result by itself. I'm going to say, what has it done for me lately? How does it match what I really think is to be true? Or how does it match what I want to solve? Right? And of course, you have to have this reference if you want to do it. Otherwise, you can't do it. And this approach here, this class of approaches here, again, the literature, are called, which I don't like, actually I prefer this, are called relative methods. Because they're just saying, construct different methods and see how they work relative to each other. My personal feeling, an idea I've come up with in about 3.5 seconds of deep thought while I'm talking to you at the same time, is that this is somewhat different from these. And I'm curious to know your opinion on this. So here's my argument. That what this is checking is not so much validation externally or internally, it's checking consistency. That your answers are all the same. So in other words, your answers could all be the same and bad. They could be all the same and good under those notions. But in both cases, you will still get, yay, stable. So my argument, which I want to throw out and have you, argue with me about is that this is doing something slightly different. What's your take? Yeah.
I view it as much more similar to internal validation than external.
That's clearly true because there's no external input coming into the system to check anything.
I mean, it's a kind of meta internal validation. in some sense.
Meta internal validation. Okay, sure.
If
yeah.
you expand your universe to include multiple clusterings,
Right.
I mean, it's kind of like ensemble internal.
So I would argue, in fact, this is called ensemble clustering. So I would argue that this third one here, where you subsample the data, is very much like that. But let me push back a little bit and say, would you say this one where you run different algorithms is also the same thing?
I mean, that's where my...
Okay, so anyone else
breaks
want to
down.
sort of weigh in on this discussion?
I have another question. Let's say you do a sample of clustering, right? Using any algorithm, doesn't matter. You have a sample. So, okay, one thing is you can compare them. What if you don't just compare them? What if you want to construct a new clustering out of the samples of clustering?
Good, we'll talk about that next week.
You know?
That's the whole plan.
Because
no,
then this
wait a minute.
stability,
We're going to talk about this next week. That's exactly my plan.
because then this stability, or verification, whatever you call it,
Yeah.
consistency,
Yep.
suddenly is not anymore.
There's a whole area that talks about exactly this point.
Yeah.
Yeah, but so we'll get to this. So yeah, so what do you think? What do you all think about this? And you've all had a little bit of experience playing clusterings now. So what do you think about like these methods? So we tried this a little bit, right? Did we do k-means with random seedings? One of the questions was doing that, right? So this is essentially a version of this, right? You can think of this as saying, the different algorithms are different seeds to k-means, and you get different answers. I haven't looked at all the assignments yet, but can you even tell me, do you get, are you getting different answers from the different seedings? I know you all produce something.
From different seedings, I didn't get a whole lot.
Non-parallel variation.
No.
Yeah.
But if you were to take something like running k-means, running agglomerative
Yep.
clustering, running different methods that we
Spectral
know are
clustering.
going to have,
Yeah.
right, very, based on the underlying structures, will behave one way or another, and we can expect that if everything is well clustered, if you have a cluster here and a cluster here and that's it, all of them are going to come up with the same thing. Otherwise, we're going to see very different results from them.
Yes.
So we can use it to verify if there are very clear clusters, we should be able to see it. If there are not very clear clusters, we should start to see differences.
So I have two responses to that thing. One is yes. That's the first response. and in the sense that, I'm glad you brought up the point of well clustering, because in some sense what these methods are doing are saying, how good is my algorithm compared to some reference point or to some internal structure? Whereas those methods are saying, how good is my data? Right? Because you're saying, is the data well clustered? Ultimately, this is a question, you're using the clustering as a lens to look at the data, whereas in these methods, you're looking at the clustering itself as your first class object. So in that sense, yes, you are saying that you want to run the different lenses of data, see if it's well clustered. But suppose it isn't. Is that a bad thing? That's the question. I mean, if I've been arguing all along that different clustering algorithms capture different structure of the data, maybe it's okay to have different answers. So even if you say that I want to see the data is well clustered, not being well clustered doesn't mean your data is ill-formed. It just means that there isn't a single unique answer to your problem. There could be multiple answers. Okay. So again, these are things that these are things you need to keep in mind when you're playing with your data, when you're applying clustering in your problem. You have to keep in mind that along with everything else as to what algorithm you choose and how you run it, you have to figure out how you're going to validate it. And hopefully, the easiest way in some sense is to have a reference. Because if you have a reference, at least you can test what's going on. What I don't know, I'm not aware of, in fact, is good methods to reason rigorously about, say, generalized. For example, in supervised classification, right? You have data, and you can give packed learning bounds. I know some of you are in Vivek's machine learning class. How many of you are in the machine learning class? So I know he's been teaching packed learning bounds, right? So you know this idea that if you assume the data is drawn from a distribution, you can see how many samples do I need to make sure the answer I get from my sampling and running my algorithm is going to be close to what the true answer is. So it's not easy to define notion of packed learning for clustering, but you can define a generative model for data. And I have to go and look and see what we can say about that, right? So that's what you'd want here. You want to say, I'm going to run my algorithm. It's going to give me some answer with respect to the true answer. And because of packed learning bounds, I know that if I take enough samples, I'll get that answer. So that's the easiest thing you can do in some sense. Or if you have a task that you want to evaluate on, then you can evaluate it directly in that. It's empirical. You might be able to say something formal, but at least you can get some results with that. But if you don't have any of those things, right? If you don't have any of this, then you have to think of other ways of going about your problem, and then you might think of these internal methods or these stability-based methods. Yes?
But for number one, clustering is basically classification.
For number one, clustering is basically classification, multi-class
So-
classification, you mean?
Yeah. So
Yes
you can-
and no.
you
So
can-
there's a semantic issue here, right? I think of multi-class classification as where labels have meaning. I think of comparing to reference clustering as not still requiring you to have labels that have meaning. In other words, it is possible for me to compare two clusterings without knowing what the labels for individual clusters actually mean. Whereas I think of multi-class classification as having explicit labels for clusters, which actually have some semantics. It's a philosophical point, I think, not so much a technical point.
Yeah,
But there's a slight difference.
Yeah, I know what you're saying. But
Yeah.
you could apply the back learning theory to that.
If you had a model, if you had some kind of distribution over your
Yeah,
clusters.
exactly.
Yes, but I suspect the BC dimension would be bad.
Yeah, but you can learn the underlying distribution, right? Okay, so you're not sure if you can say that.
Yeah, so it's an interesting question, I think. I think there's probably is work on this. I'm just not as familiar with it as I should. So, okay. Moving on. For these methods, again, there are some indices, you can compute them, or for here you can check what you want. There's nothing much to say. But if you're coming to this category of things, either this external method or this sort of stability or relative-based methods, there is a thing you need to do. You need to compare. In all cases, you're comparing. And at every level, you're saying, I want to compare a clustering to some reference. And one way to think about this in a more disciplined way is to say, I have the space, okay, so let's be a bit more precise here. So I have the domain 1 through n. Think of these as indices for the objects. I don't care what the points are, but the first point, second point, third point, whatever. And they're distinct points, so they have labels 1 through n. And I have the space of all, let's call this P, is the space of all partitions of 1 to n. All partitions. And I'm going to, for now, I'm going to say they're unlabeled partitions. Okay. Which means, so for example, if my n was 3, what's the space of all partitions? Well, so you can write something like there's 1, 2, 3 at the bottom. That means there's separate clusters. Okay. Then you could have 1, 2 in one cluster. You could have 1, 3 in one cluster, or you could have 2 and 3 in one cluster. Right? And anything else you can do? You could have them all in a single cluster. Right? Notice that I'm not saying that 1, 3 is the first cluster and 2 is the second cluster, because it's unlabeled partitions. Right? And in fact, there's a nice little drawing you can make here. We'll get to this in a bit. But the point here is that there are these 5 elements in this space. Right? The set P, P3. So we call this Pn, and this is P3. And if I want to compare them, what I'm really saying is that I want to put a distance function on the space. So rather than having a metric space where you have, in a normal metric space, we start with a metric space and we cluster the objects in the metric space. Here, the objects in my space are themselves clusterings. And I want to put a distance on them. So I want to have some function that takes 2 clusterings, C1 and C2, inside the partition, right? And I want to be able to put a distance on them. Because that's how I'm going to compare things. So this is like a meta level up. Does it make sense so far? What we're trying to do here? That instead of thinking of points in a space and in the distance, we're thinking of our objects being clusterings themselves, and then try to put a distance function on. Okay? All right. Now, you've already seen one example of this, because you've been using it in our validation experiments, right? The so-called Aversion index, the Jagged index, and so on, things like that. And they all boil down to this sort of what is called this confusion matrix. And again, we saw this in the first assignment, but I'm just going to go over it again now very quickly. So the idea is you have some kind of, you have 2 clusterings in the assignments, you had a reference and a non-reference clustering. But that's fine, doesn't matter. Ultimately, they're just two clusterings. Right? So you have C1 and you have C2. And what you want to do is compare them. And because the clusterings are unlabeled, you don't actually care about cluster identity. You just look at pairs of points. Right? So remember we had this table that said that, so for each pair of, so let's say this is C1 and this is C2. And you're just saying, points together. Well, let's say 0 means they're apart, the 1 means they're together. So points apart and points together. And again, the same thing you have here, you have apart and you have together. You get this 2 by 2 matrix, right? So go confusion matrix. And if you put a number here, right? So N00 is equal to the number of pairs of points that are apart, which is a 0, in C1, and they're apart, which is a 1, in C2. Right? And similarly, you can populate the rest of them. So you have N0, and let's say 0, 1, N1, 0, N1. Right? And there are many different methods for comparing clusterings that just take this as your input. They don't look at the clusterings anymore. They just take the clusterings, compute this matrix, throw away the clusterings, because this is all they care. And the easiest of these was the RAND index, the RAND distance. So the RAND, so there's a bit of a terminology, right? Usually in this literature, if someone says something is an index, that means a bigger number means they're closer. And if they say something is a distance, that means a bigger number means they're further apart. So usually you can do 1 is 1 minus the other. So yeah.
So now that we talk about validation,
Yeah.
I started thinking about something else. So we've seen many clustering algorithms,
Yeah.
which we run and we get a result, right?
Yeah.
And we just said that maybe internally they use some other optimization process.
Yeah.
But when we validate it, we use some other
Yeah.
some other validation techniques to validate it. But we are unable, I think, in all of the algorithms that we've seen so far, to tell the clustering what did he do, what the clustering did wrong. You know what I'm saying? Like to tell the clustering, like to propagate the information inside so that he can continue or to improve that. So all we can do is just restart the clustering.
That's not true. We have seen one method that does it.
Oh, what does that? Oh, maybe I just forgot that.
Think, anyway. We have seen a method that allows you to incorporate information about what was wrong and what was right. Maybe not in the best way possible, but there is a way to do it.
You mean the information theoretic?
No?
I don't remember.
Anyone? So in other words, I have information about, pairs that were wrong or right, let's say. Can I design a new algorithm that will take into account information? I mean, it's not going to be perfect. It's not going to do exactly what you want to do, but it has the ability to do it. We've seen one method that does this. Anyone? It's called correlation clustering. What do you do in correlation clustering? You have pluses and minuses, do you not? You say these points we think they should be together, these pairs of points should not be together. And we say, okay, cluster that information. It is the only method we've seen where you have both positive and negative labels essentially on pairs of points. You could imagine doing that here. You have some reference, you look at things that are mistaken, right? You look at things that are wrong. And now you say, oh, I'm going to run some kind of correlation clustering on this now. I said, it's not going to be perfect. Because now, like, oh, well, but I have the original geometry, I have this correlation, I'm going to put them together, I don't know what to do. But there's at least something there you can start with to think about. To use that information that where you have misclassifications and positive classification and try to use that. So there is a way to do it. It's not perfect.
Yeah, because, okay, but putting aside, or let's say there are algorithms.
How about you continue? We'll get this. Okay. So the first measure of similarity or difference, whichever way you want to see it, is the RAND index, which basically is the generalization of accuracy for a binary classifier. Right? So if you constructed such a matrix for your two clusterings, what is your ideal matrix? What does it look like? It's a 2 by 2 matrix, right? And imagine these are normalized. So I'm going to divide this by what? What should I divide this by to normalize everything?
N0.
That's it. So you n choose 2. Why? Because I n choose 2 pairs of numbers. So yeah, so these numbers are all between 0 and 1. So what is my ideal answer? So if C is equal to the reference clustering, right? What should my matrix look like?
N10 and N01 has to be
Sorry? Yeah, go ahead.
N10 and N01 has to be 0.
Well, if these have to be 0, then just by calculation, these have to be 1. Right? Because the sum has to be. Do you see why? So basically, you agree on everything. When they're apart, they're apart. When they're together, they're together. And this, now, so if you want to design an index of accuracy, what you're saying basically is that the bigger these numbers get, the worse your answer gets. Right? Notice that the sum is a constant. So if these are getting bigger, these are getting smaller. Right? So if you want an index of quality, which is basically a number that's bigger if they're better, you're going to basically say your index is n00 plus n11 divided by n choose 2, which is the sum of all 4 of them. And this is, of course, the random index. A related notion called the rand distance is 1 minus this. And it is a metric. Right? Easy enough. There's a related notion called the Jagged Index, which again you've seen. Does anyone remember what the Jagged Index is? I'm asking because I've forgotten it.
Something to do with intersection versus union.
It is. So that's right. So the Jagged Index basically is the following idea. So the rand index is talking about accuracy, right? The Jagged Index, the picture you should have in your head is this picture. Okay. If you want these two Venn diagrams, these two sets get closer and closer together, what's going to happen? The intersection is going to get very close to the union, right? So that's the picture you have for the Jagged Index. And there are many different ways in which this shows up in the literature in different communities, but they all boil on the same idea: intersection divided by union, right? So you basically want to say, that I want that the Jagged Index is big if the intersection divided by union is big. But what does that mean here? We have pairs of elements. What does it mean for intersection over union to be big? What you're saying, sorry, anyone?
Has to be the sum of N00 and N11.
Well, it's not. This is the difference. Since you're talking about intersection over union, the union means the set that you can see. And in some sense, you only see things that have at least one in them. You're not seeing the things that are not in the same cluster in either of the two. So if they're not in the same cluster in either of the two clusterings, they don't exist in something. They're never going to be put together. Right? A pair only shows up on a blip if one of them shows up or in both. So that's why the Jagged Index, as an intersection over union, becomes the intersection where they both agree, which is this, divided by the sum of these three things. Okay. And again, 1 minus this is the Jagged distance. So it's slightly different, right? So first of all, you're not including this. So it's almost like you took this quantity. If you added n00 to the numerator and denominator, you'll get that. So it's related, but it's different. And of course, if this number gets very big, the problem is if this number is very big, then this is going to get drowned out by this value. This is a bit more subtle of a more sensitive test, right? So that's one way to think about what's doing. That if you have a case where, for the most part, they agree that they don't have too much stuff in this section here, then the rand index is not going to be a good distinguisher, whereas the Jagged will be. Because it's focusing on the parts where they're actually saying something, not the parts where they're both quiet. Okay? So you can think of the Jagged as being better when you have just a few places where they're actually saying anything, and the rand being a good example where there's lots of chatter, saying and not saying, the sort of equal amount. There are other variations on this theme. There's another interesting one that I've been pondering what it means. So let me see if I can get this right. So this notation of this thing is very important. So this is called the Folks. This is the Folks-Mallows index. And it looks like this. It's some kind of geometric mean of two ratios. And the ratios are so this is unfortunately this is asymmetric. Well, no, it's not asymmetric. Yeah, no, it's fine. So it doesn't matter. Okay. Question for the audience. What does this even mean? So basically, if you think of what's going on, it's taking two ratios. One is the column ratio, yeah? And one is the row ratio. This divided by this sum, this divided by this sum. And it's taking the geometric mean. So think of some kind of average. There's no reason why, this thing you could also imagine this plus this divided by 2, but some kind of average. The average of these two conditions.
It's kind of a geometric version of S-score.
Explain.
So, I mean, assuming that one was a real one.
Yeah, good. So let's say this was the real one.
Right.
Yeah.
Then what the column is recall, and what the row is precision.
Very good. So let's try to unpack this a bit more. So the column is this one is the real answer, and this is the answer we are getting from the algorithm. What John says is that this is recall. Recall, remember, is the number of stuff of the true answer that you get, right? So when you're doing a search, you want to know how many of the right answers did I actually get. These are all the right answers because in the true answer they're together, and these are the fraction that you're getting. Very good. Thank you. That was very helpful because I was getting confused with this. So this is recall. The row is precision. What is precision? Precision is in my answers that I got, how many were good. So precision is in fact, if you think of the first page of Google search results, precision is very important because people don't go beyond the first page. So you better make sure that in the first page you get as many good things as possible. So Google cares a lot about precision in the first page. If Google actually give you the entire list of results, then they might care about recall. And recall is good for certain applications, but for a lot of these search type applications, because people are impatient, precision is often the more important thing. In a short span of what I get, how many of them are good? So this is recall precision because you're saying, these are the things I get, how many of them were good? This is precision. It should be clear that you can trade these off against each other, right? If I always return all possible answers, my recall will be great. My precision will be terrible.
I think so.
Yeah, right. Especially if I generate a bunch of crap, right? Conversely, if I only return if I return just a couple of answers, my precision will probably be decent, my recall will be terrible. So there's a trade-off. Just like all kinds of trade-offs in this area, right? There's a trade-off between how liberal you want to be and how it's like type 1, type 2 error, or p-values versus power versus sensitivity. No matter how you want to explain it, it's the same dynamic happening here. And so this is basically saying that I just want to balance precision recall in some reasonable way. There's nothing stopping you from saying I want to recall plus precision divided by 2. Is that the F-score? Or is the F-score the harmonic mean?
S-score is harmonic.
Yeah, so this is the Folks-Mallows. The F-score is the harmonic mean of these things. And there's an argument to be made that if you're averaging probabilities or ratios, you should take the harmonic mean and not the arithmetic mean, because the denominators are actually whatever. So you can think of S-score as 1 divided by 1 over recall plus 1 over precision. And if you remember your basic rules, we know that, let's see, the harmonic mean is less than or equal to the geometric mean, which is less than or equal to the arithmetic mean. Have I got this right?
No.
No? Which is where is it? Sorry.
AM is greater than GM is greater than H.
Did I just write that?
Arithmetic mean is less than. It's
Which
greater
is
than
the same thing I
GM.
wrote.
Yes, it's the same.
Okay, so it's subject.
Yes, it's the other way.
The
AM,
S score
GM
should
greater
have
than
a-
yes.
have a 2 in the numerator.
Pardon me?
The S score should have a 2 in the numerator.
Yes, because you're taking the harmonic mean.
Right.
You should get 2.
It's 2 times the sum, the product divided by the sum.
Yeah, that's right.
No, it's-
Yeah. It's the GM divided by GM squared divided by AM or something like that. Yeah. Which is equal to 2 times the well, 2 times the geometric mean squared divided by the, well, fine.
Why don't you just R?
So the F score, the harmonic mean times the arithmetic mean is equal to the square root. So yeah, but we all. So that's where this comes from. So this is the geometric mean of precision recall. The F score is the harmonic mean of precision recall. There's nothing stopping you from taking the arithmetic mean of precision recall. Okay? But that's what's going on here. That you're here's an important point to make, right? These methods, apart from the random index, are very, in some sense, explicitly saying there's a good answer and there's our answer, and you want to compare. Right? The random index is a bit more, egalitarian. It treats these two the same way, right? Whereas the other methods treat this very differently from this. So these methods are actually not that well suited for distance calculations just between two different things. They're very well suited for a reference versus an answer. And you got to make sure the order is correct. You want the reference to be on top because you want N11 to be accepted. You don't want to be replacing these two things. Okay. So these are all ways of comparing two clusterings. And in some sense, they do give you a distance function because you can take, for some of these at least, you can take 1 minus. There's another one that I want to bring up actually, which is very, very popular in the world of clustering, which is called normalized mutual information. And the idea of NMI is again, because it's information that's a bit more involved, but it has some interesting properties. So what NMI is trying, so all these methods are very discrete. And they say, okay, our 2 points together, are they different? We're not going to say anything else about it. NMI is trying to look at things a bit more holistically. Right? And so you can imagine a cluster of your reference points. So you have a cluster of not reference, you've done a clustering with your algorithm and it's got some points in it. And you can imagine, let's say there were 2 clusters in the correct solution. And in your clustering, it looked like, it had some of the points that the true clustering called blue, and some point at the true clustering called red. And similarly in your second cluster, you had again some points of the true clustering called red, and some points of the true clustering called blue. And if you look at this, you're like, well, they are clearly very, very different. What I should have been doing was partitioning somehow this way to get the true cluster, not the way I did it. NMI is trying to capture this idea that somehow there's a lot of confusion between your clustering and the true clustering. Notice that I didn't need to know what the labels are. I didn't need to know that, okay, my clustering number 1 corresponds to blue, or should correspond to blue, or my clustering number 2 should correspond to red. I don't care. And we'll see why, how to write this down so we don't care about the actual mapping. There are versions of these clustering comparisons where you need to know, okay, clustering label 1 was really clustering labeled 5. Those are not very good because then you have to figure out the mapping first before you can do any calculations. Here you don't need to do that. So how do I capture this idea, right? How do I capture the idea that they're somewhat different in an information theory? One way to think about this is to say, imagine the clustering as some kind of distribution. Right? So let's say I write down a clustering. So I have some clustering, and we've seen this before, so you're not unfamiliar with this idea, right? That I have 4 clusters and they have different numbers of points in them. Right? You can now say, if I take a random point, what is the probability that it has cluster label 1? Or does cluster label 2? Or cluster label 3? Or cluster label 4? Right? You can ask that question. Right? So you can say, okay, if there were, say, so you have n1 points here, n2 points here, n3 and n4, the total is equal to n. Then the probability that the cluster label is equal to 1 is equal to n1 over n. Or at least can be modeled by n1 over n. Right? I'm being very horribly frequentist in this, but let's just pretend that's okay for me. Right? So you can think of this as representing a distribution of some kind. Okay, so I have one distribution for my clustering, and I have a similar distribution for my reference clustering. Right? Yeah. Okay. How might I try to compare? So if I have two distributions, and I want to compare them, right? I want to see how similar they are to each other. The information theoretic way to ask that question is to say, what is their mutual information? How much information can I learn about one clustering from the other? Suppose they're identical, okay? That this clustering is identical to that. Suppose I took a sample from here and looked at its label. Does that tell me everything I need to know about the label in this other one? It does, the deterministic mapping, right? This cluster 1 is this cluster 5, and I know exactly what to do. So you can think of the similarity between two clusterings in this information theoretic way. We're saying if I sample from one, what does it tell me about the other? And we've seen this already with information theory. That somehow the mutual information is what captures this idea. But how do you define mutual information here? So now so for mutual information to work, you need these conditional probabilities, you need these probabilities on the side, but you also need conditional probabilities. You need to be able to say something like, what is the probability of, we need to be able to write down numbers like this. What is the probability that L1 is equal to 1 given that L2 is equal to 2, right? The interpretation of this statement is that well, let me rewrite this. Let's say LC is equal to 1, given that L reference is 2. Okay? So let's say these are my clusterings, and L reference and L something. Let me say this better. Sorry, let me just use this picture so I can use this the right way. So that L reference is equal to red, given that L clustering is equal to 1. Right? So what is that probability? Well, it means if I sample from cluster 1, what is the probability of seeing a red point? In this case, the way I drew it is going to be something like half. Right? And you can write down appropriate the 4 numbers for each value of red and blue and 1 and 2. But those are conditional probabilities, right? If you think of this again as a random process, I'm not saying they're real probabilities, but if you pretend it's a random process, then these are probabilities. And once you have conditional probabilities, you have mutual information. So what I'm going to do is define the mutual information between the two distributions on the labels induced by the two clusters. And so we know how to write mutual information if I have two distributions over a domain. If I want to write the mutual information, it's basically a sum over I equal to 1 to k1, but the number of clusters in the first clustering is k1. Sum over j is equal to 1 to k2, where k2 is the number of clusterings in the second clustering. Number of clusters in the second clustering. And it's something like, P of L1 is equal to I, L2 is equal to j, the joint probability, times the log of, this again, the joint probability, L1 equal to I, L2 equal to j, divided by probability L1 equal to I, probability L2 equal to j. Right? And if you read this expression, what you're really saying is that, again, by putting in actual numbers, you're basically saying the number of elements, the cardinality of Ci intersection Rj, right? This is the number of elements in there, divided by divided by n times, this be n squared, should this be n? There should be I feel like there should be n squared for homogeneity. times, again, log of, when this all will cancel out, you'll get Ci intersection Rj divided by product of Ci cardinality. I should excuse me, check that whether the fracture of n is correct or not. But the basic idea is you look at the fractions. You look at the fractional values of these things and you put them in there. And this number should be large if they're the same clustering. Because of the same clustering, again, all these numbers, the KL divergence between the joint and the marginal will be 0. And, well, sorry, it'll be very large, and you'll get a big number. That'll be the right answer. And if they're completely messed up, there'll be no information you get from one from the other. There's no mutual information, this number will be 0. And we've seen this already, in the context of information theory. So while the mutual information, so now I can define, what I've basically done is I've cheated, right? I've taken two clusterings, treated them as distributions, and computed their mutual information. Treated them as a joint distribution, rather, and computed their mutual information. But this in itself is not enough, because this number I can make arbitrarily large by making the clusterings just look very different. Or just separate things out. And so normally what you do is you normalize this, so you compute the mutual information of the two clusterings, and you divide it by the average entropy. So you remember how we compute the entropy of a clustering? You look at the fractional values and you compute the entropy of this distribution. So you compute the average entropy of the two. This is called normalized mutual information, or NMI.
Is that normalization what's controlling for the disparity?
Yeah, and also the fact that you can sort of trivially make things more and more refined, and it will look good. Yeah. It's a normal, yeah. Okay. And I want to point out a couple of things, and I should have pointed this out earlier, but I want to point this out now. That in none of these methods do you actually care whether the two things you're comparing have the same number of clusters or not. Which is actually very important. Nowhere am I using this fact. Even in NMI, I'm not, K1 and K2 could be very different. I don't care. Okay? Because I'm always looking at these co-occurrence probabilities. I'm just looking at pairs of things. I'm never having to look at anything more than that. That's true for all these measures. So again, I don't think, as far as I understand, NMI is not a metric, in that you can't use NMI or its reverse, 1 minus that, to give you a metric distance on clusterings. But it's a good index for measuring or something. Okay, if you actually want distances, and we will want distances, we have to do a bit more work. Okay. Any questions? There are other measures that people have come up with, but I think these capture in some sense, RAND captures the basic accuracy notion. Jagged and its relatives, like these, capture this whole precision recall distinction you want to make. NMI captures this more information theoretic view of what clustering represent. And so they have their own. There are others that, like I said, I've done some work on this, but we don't talk about it. So you have your index, great. I just ran my index calculation, and I realized that under the RAND index, so I'm going to make a table. So I'm going to take my clustering, and I take my reference clustering, and I make a table. So I have RAND, I have Jagged, I have F-score, and I maybe have NMI. Okay? And I get a whole bunch of numbers, right? So let's say, remember, numbers are bigger if they're better. So this is 0.8, 0.7, 0.9, and 0.85. Should I feel happy or not? Have I matched the reference clustering or not? The maximum value is 1, lowest value is 0. Is this good? Yes? Nitin says it's good?
Yeah.
He's happy? Why are you happy?
Yeah, looking at the others, when I have calculated the RAND index, Jagged indexes, for other clusterings, and these numbers look good.
They look good.
Yeah, compared to other numbers.
Compared to other numbers.
Yes.
So if I just give you a whole bunch of 0.1s, this will make you even happier?
Yeah.
Okay. So compared to other numbers, they look good. Okay. Anyone else have any thoughts on this table? Should I be happy with this table with my clustering?
My org was Newton, so.
So your method is to ask Nitin. I see. Okay, this is a different procedure altogether, but it is surprisingly common. Okay. So Nitin says yes, John says whatever Nitin said, and anyone else say say about this?
I mean, based on the experiments we'd run in the homework.
Good. Tell me what you've done.
You've got the RAND 0.8 seemed like it basically, that was a value that basically gave you like a Voronoi spreading of the data cluster.
Explain. This is very interesting. You just use words that are very pretty.
I basically, if you think about when I got RAND indexes of 0.8 and Jagged indexes of 0.7,
Yeah.
even if I could see what appeared to be various clusters within the data, the results I wound up getting in my clustering were simply just treat all the data points as one large cluster. Now assume you want 8 clusters out of it. How do you create 8 clusters out of it? With k-means, that means that they're going to be equal size, which is effectively going to be a Voronoi region
Sort of, yeah.
division. That was the sort of result I was going
So
to
wait,
get.
but wait, I'm confused. Are you saying this is good or bad?
I'm saying it's going to depend on what you know about your underlying clustering or don't.
Okay. So you're saying you cannot give a determination at this point?
No.
Okay. Good. That's another good answer.
They're basically taking C1 and C2 and making a comparison between both the clusters. Both are bad. Both are not wrong clusterings as opposed to what.
I know, but I'm saying that you get these numbers, right? I mean everything in the abstract. I mean, I gave you these numbers. Now what do you do?
Then it is, in spite of the RAM index being high, it does not give us the correct information about the cluster.
So you feel suspicious about these numbers? Okay, fine. Are you less suspicious? So like any good, grad class, the goal is to completely confuse you. It's not to teach you. And the point I'm trying to make here is not that there is a right answer for this. It's to ask you to think about how you decide what a right answer is. How do we decide what a right answer is? I'm not saying that 0.9 is better than 0.8. I'm saying, how do I even begin to think about the way to reason about this? That's what I'm trying to get at here. I don't know how to reason about this. Maybe Nitin will leave and I won't be able to ask him anymore. Then how will I know what's right or wrong here? I have to have some way to do this.
Take the average.
You can take averages. Sure, you can run this a bunch of times and try to get some sense. But even then, you might get a very high confidence number. You still don't know what that number means. I might run this for 10 different methods, different random seeds, and get a RAND index that's concentrated between 0.81 and 0.82. Fine. That still doesn't give me the answer to what I want. And so the problem that you have to deal with then is that how do you come up with the baseline for this? Right? What is a baseline? What is good? What is, maybe the average value for this over random things is 0.8. So everything has to be measured in reference to 0.8. What do you do? So in fact, this is the thing. You have to, so if you want to be able to reliably figure out what these things are, you have to assume some kind of baseline model. For example, you could say points are assigned randomly to clusters. Okay? You could say if I assign points randomly to clusters, what will the expected value of any of these indices be? For NMI, I'm willing to bet it's going to be close to 0. But again, there are estimate issues that are really small. Because if you assign points randomly to clusters, there's no information in the system. So you should get a number that's very close to 0. But you can estimate that. You can actually assign points randomly to clusters a bunch of times, look at the estimate for what you get. Right? So for all of these indices, right, it's not even enough to just compute the index or to do all this work. You have to be able to give it a sense of proportion. And the way you do that, usually, so what you do is, with any of these indices, doesn't matter which one you pick, you fix a baseline. Fix a baseline distribution. Think of this as a poor man's p-value testing. Right? The way you do p-value testing, much discredited as it is, we won't get into that, is that you have some sense of a distribution over outcomes, over normal outcomes. They don't have any signal. And what you're saying is that, I got this outcome. If my data was had no signal, I should not have seen this outcome. Or so I would have seen this outcome with a very low probability. So I feel like this is a rare occurrence in the world of normal data. Right? I mean, there may be some things about does this actually say you have a signal or not, but without getting into all of that, what you're trying to do is recreate the same thing here. You create some baseline distribution of data with no signal. What is data with no signal for clustering? Random clusters. And you can define this in many ways, right? You can actually just say assign data to clusters randomly, or if you have points in a geometric space, put points randomly in the space. There are many ways you could think about this. They're not all obviously good or bad, they're just different methods. Fix some distribution and then estimate the expected value of your index. Whatever index you pick, right? You can now compute on the random data. You can do it a gazillion times, take the average. This gives some expected value. Once you do that, you have a little bit of a better handle on what's happening with the actual value of your index. For example, you could do something simple like saying I'll take a linear scale. I'll say that my modified index, I, is equal to the value I just reported on my data minus the expected value. Right? Divided by the max to min range. And the max to min range is often, I minus the you want to normalize this somewhere. So the way to normalize this is to say so you can look at the max value by the expected value. Right, so what you're saying is that, okay, I have some data, I have some value of the index, and this is the expected value of the index. My value is here. This is the maximum range for my data. So I'm saying, let's look at how far away I am from here relative to the whole range. That's one way of thinking about this. And so if I'm really close to the high end of the range, it's like saying that again, if I look at a distribution over this, I'm somewhere out in the table. I said this is very simplistic because it's very first order. I'm just looking at the expected value. You could imagine being a bit smarter, right? You could say, okay, I will look at the variance of this value, try to fit some kind of Gaussian to it, and then or some kind of other distribution to it, and look at that in that sense. This is again, like I said, a poor man's p-value. You're trying to get something more rigorous. So if you really want to pay attention to these numbers, you have to do at least some kind of simulation like this. So now we don't actually know the two distributions, but luckily we can simulate it a bunch of times and try to find this estimated value. So you can do like bootstrap or permutation testing or all these other methods. But you need to do something like that, otherwise those numbers don't mean anything by themselves. And so once you have such an index, it's not hard to transform it to a sort of a normalized index. Right? It gives you the right scale.
Can you run large-scale simulations and come up with the underlying distribution of any of these?
Well, you can do simulations, come with an empirical description of it, yeah, sure, and that's exactly what you'd use here. Analytically, if you want to do it, I don't know, that would depend on the problem, on the particular measure you use. Yeah. But yeah, sure, you can always estimate these things with the appropriate number of samples, right? That's exactly the basis of the bootstrap. That use simulation to replace an analytical reasoning. So then hopefully you see why this is important to do. And I should say, up front that people aren't always that careful about doing this. They'll come up with an index number, and what happens is over time, as you've been seeing, you build some intuition about what numbers are good or what numbers are bad, and then you use those numbers. Ideally, you should probably do something this more carefully. But I think it's good to remember that, even if you don't do it yourself, at least remember the dangers of not doing it. That you don't necessarily have a good reference for what those numbers for your indices actually mean. Any questions? So I'm curious how many of you have encountered sort of needing to do some kind of clustering in your own work where this became an issue. And maybe you didn't have a way of saying this precisely, but now you can recognize, okay, this is what I was trying to do. Has anyone ever come across this kind of thing? I mean, we've been talking about cluster validation for a long time. All the work we did on data collection was precisely to get a ground truth reference so we could compare it. So we've seen, then you saw this on Tuesday, those of you over here, that we had to do a lot of work to get some reference labels for this data we had of, the professors in what area they are and so on. So it took some work to do it. And that's why we need it. And a lot of good work in the community is building good reference structures. the UCI database, for example, is an example of good reference structures you can play with, because it's got ground truth access to it.
So the work which I am doing, it involves this thing, right?
So
So
explain.
coming up with a baseline estimation and then
Can you say more about
so it's like you have some random points and
Yeah.
I mean distributed geographically, and you know the coordinates of those points, and you know that and there are some points working properly, and then you mark them as red, and then they are not. Those are working properly are marked as blue.
Okay.
And then you have a separate classification, fixed classification. Okay, these points are red and these points are blue,
Okay.
and then you basically don't know where the cluster is, and the cluster is basically which contains all the mostly the number of red points.
Okay.
So I don't know where the cluster is, and I want to find this cluster. So basically what I do is like I basically first create the random data set, a uniformly random distributed points, and
Yeah.
then I come with a similar baseline distribution.
Yeah.
I basically simulate my algorithm like 1,000 times, and then
Yeah.
come with the probability distribution. I take the 95 percentile value of it,
Okay.
and then I find this is the thing which is my baseline, and then I implant a cluster knowingly. This is my cluster now, and then I apply my same algorithm. I
And see if you find it.
yes, and see, and there is basically a score. The score which is like
Yeah.
by which I came up with this distribution, and then I calculate the score of both these things, and I say the score for the true cluster is more than the baseline score.
Yeah.
Okay, I found the cluster now,
Okay, great.
and this is significant cluster. So this kind of.
That's right. Yeah, like I said, this is merely the application of basic sort of p-value principles to this problem of validating the index score for a comparative clustering. So in that sense, you should be seeing this showing up in many different places like this. So it's not a new thing, it's just that applying an old theory to sort of similar. Okay. So no more questions. I'll see you all next week, and we'll continue our discussion of validation and also distance calculations and the discussion of what is called consensus clustering, finding a common clustering among a bunch of different things.